Okay, well, welcome back to episode 1 of season 2 of the View Dependent podcast, where we speak to guests all about lifelike 3D and its role in the rapidly emerging industries surrounding everything around novel view synthesis and simulation. So, today I am very excited to welcome everyone back to our first episode in a little bit over a year. We are here with Jan Held, as well as my co host, Mr. Nerf, otherwise known as Janusz.
Hello. Hi. Hi, Jan. Nice to meet you. I'm glad to have you here. I'm super excited to hear your opinion about Gaussian splatting and alternative primitives and what we have to expect in the future if Gaussian splatting is the final destination or if you laid out already the new way of doing splatting. So I'm very excited to have you here. Thank you very much.
Yeah, hello everyone, and thank you very much for having me. It's really, really nice. I'm a big fan of your podcast and all the work that you have been doing over the last years. It's like really, really impressive to see like the huge community you have obtained over the last years. And I'm a big fan of yours, so it's really nice to be now on the podcast.
Of course. Yeah, literally we only have, stuff to talk about because of the research that you are doing. And so, we're really excited to have you on as well. So I think to actually just go ahead and get started with it, let's actually go through a little bit towards the beginning and talk a bit about your background and like what you were doing when you first stumbled upon Radiance fields. You still like remember when you first saw really lifelike 3D?
Yeah, definitely. So at the beginning, like the first time I came in contact with research, it was for my master thesis. And at that time, I was still like a football, like a soccer referee for the American people. And the first time I did research, it was completely on soccer and building like an AI that can like detect fouls, penalties, yellow cards, and red cards. And that was also like the first 6 months what I was working on during my PhD. And then I went to KAUST, the King Abdullah University of Science and Technology in Saudi Arabia, and they organize a Rising Star in AI symposium every year. And there was Jonathan Luton, who did dynamic Gaussian splatting, and he presented his work, and it was just amazing. I was really impressed of how good Gaussian splatting is working and how nice it looks like. And that was the first time that I really came into contact with radiant fields, Gaussian splatting, and all of this amazing stuff. And that's when I also decided that I want to go in the direction of 3D and novel view synthesis.
How did you actually get started? So after you saw the talk, so you went about doing a research project, or how did you get started with Gaussian splatting?
So I had my funding for my football soccer research, and that's also how I started my PhD. And then I just switched completely from going from soccer and doing computer vision for football and switched to 3D. And that's the nice thing in Belgium. If you have like your research funding, it's not that you really have to do like the topic that you choose and just follow it for like all the years, but you have like the freedom to switch. And my supervisor also gave me the freedom that I can pretty much do whatever I want. And I'm really grateful that he just gave me all the freedom. And so I just moved from like football and soccer to 3D reconstruction.
Nice. And so you came into it already, with Gaussian splatting and dynamic Gaussian splatting at that point being published. And when you first started to get interested in it, like what made you start to think through like alternative primitives leading into your 2025 paper, Convex splatting?
Yeah, so initially we actually wanted to do novel view synthesis in football, like such that it is a little bit still in the same domain as what I was working, but it's quite difficult to do it in football, or especially like 2 years ago, because you have like 10 cameras in the stadium. All cameras are like at a different distance, so it was quite difficult to do it, and we also didn't have the data. And so we were just thinking about what else could we do with Gaussian splatting. And at that time, I was working a lot with Silvio Giancola. He's a research scientist in KAUST. And then he came up with this paper called Convex Net, which reconstructed simple objects by using convex shapes. And then we were like, oh, wow, that looks super nice. Why has nobody ever tried it to do it with Gaussian splatting and just replace the Gaussian and use a convex primitive for the reconstruction? And that's actually how like all this project started. Yeah.
And you obtained really nice results with the paper. So what is the difference between Gaussian splatting and convex splatting, and where does convex splatting excel? Where is it better than Gaussian splatting?
Yeah, so the main issue that we found with Gaussians is that it has this like this smooth nature. So in the center you have like this full influence. And then like if you go further away from center, it's getting smoother and smoother until you finally have like no influence. But that has like a lot of downsides. For example, if you want to reconstruct like flat surfaces or sharp edges, like the sharp edge of a table, then you really need like a lot of Gaussians to really get something sharp. And with convex splatting, we had two parameters, which like the first parameter, it influences the smoothness of the convex. So we could have very smooth convexes, exactly like Gaussians, but we could also have like very sharp edges, such that the convex can really represent sharp edges of objects. Then we also had another parameter, which makes the convex round or sharp. And with those two parameters, we could at the same time reconstruct Gaussians, but we could also reconstruct like fully like triangles, rectangles. And we tested everything on a simple 2D toy example. And with convexes, we could just reconstruct every shape that we could think of. While for Gaussians, you really needed a lot of Gaussians or 2D Gaussians to reconstruct a simple triangle or a simple rectangle. And that was basically the starting point that we also wanted to do it in 3D.
Yeah, I remember you showing an example of like a chair being reconstructed with like Gaussians as opposed to convexes, and you were really able to drop the primitive count like significantly using convexes, right?
Yeah, definitely. I mean, they can pretty much reconstruct it whatever you want. And even if you increase the number of vertices that define the convex shape, you can pretty much reconstruct all the shapes that you want. And it has just a lot of advantages over the simple Gaussian primitive.
Does it also have disadvantages, or is it like better in every aspect?
No, I would say definitely in speed, Gaussians are faster because for convex splatting, what you have to do is to calculate the convex hull in 2D, which takes a little bit more time. So convex splatting is slower than Gaussian splatting. And also maybe for optimization, Gaussians are a little bit easier because everything is smooth. So it's just maybe a little bit easier than for convex splatting.
When we take a look at optimizations and computer graphics as a general industry, there's probably no shape that's been more optimized than triangles, and that's kind of like where you started to turn your attention to. And I'm curious, like at what point did that like curiosity start to translate to? I wonder if we could just make everything go return back to triangles and really leverage the history of computer graphics.
I think there were like two reasons why we went towards triangles. The first one was that we didn't want to calculate the convex hull anymore because it was just slowing down the training and the rendering. So we were like, hey, if we just remove the number of vertices to 3, we just end up with like a surface primitive and we can just skip the convex hull and we are much faster. And if you reduce the number of vertices of a convex to 3, you end up with a triangle. And then we were like, oh, wow, okay, nice. If you also have a triangle, then it's also like deep primitive that all like chip user optimized, like a mesh is a triangle. And it has so many other advantages that we don't have if you have like a full convex with multiple vertices, and also what we don't have with Gaussians. So it was like multiple things pointing towards the direction of going towards triangles. And I think eventually it was also definitely the right choice.
So I think when you switched to triangles, was there something which broke like immediately, or was like straightforward after you had your experience in your implementation of convex splatting? So was it like a very smooth transition into triangle splatting, or did something not work out as planned?
I think if you just take convex splatting and you reduce the number of vertices to 3, and you just optimize, it also works to some extent. But the issue with convex splatting was that the indicator function. So basically, what we do is, so if you have a triangle, what you do is you calculate the distance to the edges of the triangle, and then you take the minimum distance, and then you can determine if you're inside the triangle or not. And for convex splatting, we were using a sigmoid function, which is 0.5 at the edge of the triangle, which means that the influence of the triangle is no longer bounded by the vertices, but it can be much larger. And that was just a big issue during optimization because sometimes the triangle was super small, but its influence was like over the full screen. And then if we want to do splitting, we were just checking how much influence the triangle has on the image. And then we were splitting triangles, which were already super small, but the extent was just large. And then just optimization was super strange, and we had like a lot of very strange artifacts. And so it took quite a long time of finding the right indicator function, which really bounced all the triangle influence inside the triangle and that we are not leaving, or like the influence of the triangle does not leave the triangle. But we also wanted that the center of the triangle always have a full influence of one, such as Gaussians. So it was like a little bit of work of finding the right indicator function that gives the best results. That was, I think, like one of the main challenges for triangle splatting.
And I'm curious because, in triangle splatting, you have three main variables that you pay attention to. You have color, you have the smoothness, and then you also have opacity. And so I was actually kind of curious if you could talk through about how each one of these three items contribute to one another in the actual reconstruction.
I think they are pretty similar to how they impact also the Gaussian splatting trading. I think for triangle splatting, they were free to be optimized, so there was no no regularization on moving the opacity towards being fully opaque or stuff like this. So they could just be optimized as they wanted. I think it just had the same impact as for Gaussian splatting.
At this point, I think triangle splatting is very similar to Gaussian splatting, it's just like a different primitive. So are there like major differences? Is it harder besides like, I think you had like invented, is it your invention or is it something you referring to, the window function, I think, right? This is like the main contribution of this paper. But is there something else like very different, or is it just like a different primitive at this point of time you're optimizing?
So yeah, I think triangle splatting is pretty similar, especially to 2D.js. I mean, both are like a surface primitive and are trying to improve the geometry. So I think both of them are definitely very similar. I think that triangle splatting achieves a nicer visual quality than 2D.js. But overall, the difference is not like huge. So it's like very similar. I think we made a couple of changes about the optimization of how we optimize the triangles. So we modified the MCMC optimization strategy. I think like 3D.js or 2D.js, they just use the opacity to find places where you have to add Gaussians, but we also took into account our smoothness parameter, because usually in the background we found that our triangles are less smooth and more like more discrete triangles than in like the middle of the scene. And so we also use this smoothness parameter to determine where we want to add triangles, and this also helped quite a lot for the performance.
In the later stages of the original triangle splatting paper, you began to force all the triangles to be opaque, I think in the last like 5,000 or so iterations of training. And then you followed up with another, triangle splatting paper, Triangle Splatting Plus, that took a little bit of a different approach in terms of the opacity of the triangles. And I was wondering if you could talk through a bit about what you've learned from that.
Yeah, so for triangle splatting, we just did it like very naively, just like the last 5,000 iterations, just increased the opacity to get fully opaque triangles. It was like, I think, a couple of days before the deadline, and we just wanted to show that you can put it into a game engine and run it like at like a very high frames per second. So it was not like really an optimized strategy. And then for triangle splatting, we were really looking in, for triangle splatting plus, we were really looking into how we can actually train triangle splatting such that we end up with fully opaque triangles but still have a higher visual quality. So instead of just doing it for like last 5K training steps, we really did it like slowly over training, such that the triangles have more time doing optimization to adapt towards getting opaque.
And what is the difference between triangle splatting and triangle splatting plus? So what is the difference? I think you have more something which is called connectivity and meshing. So what is this? And how is it maybe different from canonical meshes, which you usually get out of Blender or something?
Mm-hmm. So the main difference between triangle splatting and triangle splatting plus was that triangle splatting was just designed to get like a high visual quality, exactly as like 2D.js, 3D.js. It was like a completely splatting a project where you just wanted to get high visual quality, while triangle splatting was more towards the direction of what can you do after you optimize your scene, and how can you easily put it into a Blender, Unity, or just use it like immediately after training for downstream applications. So like the main challenge that we had to fix was that we want to have fully opaque triangles, as they are like as they can be just rendered much faster as those semi-transparent and like smooth triangle. So that was like the main difference between Triangle and Triangle Splatting Plus. And for Triangle Splatting Plus, we also went or wanted to go towards the direction of connecting triangles. So we changed the parameterization of Triangle Splatting Plus such that each triangle does not has its own vertices, and then we just individually optimized the triangles, but we created a set of vertices, and each triangle was then just defined by the index of the vertices that it was using. And by doing this, we could just connect triangles, and then all the gradient was always flowing back to the vertex from all the triangles that were connected to it. And so how did we do it? So we just did a Delaunay triangulation at the beginning of the training, such that we get like a connected mesh, and then we just optimize this for 30,000 iterations to just get like a much higher quality. But we also included densification and pruning, and that has then as a consequence that some connectivity between the triangles, as we just remove triangles, the connectivity just got lost, and eventually at the end of the training, we still had some connectivity, but it was not like a fully nice connected mesh. So if you compare it with like the traditional meshes, ours is not watertight, and the triangles are still intersecting each other. So it's like a step towards building a mesh, but it's not like a fully connected, watertight, nice mesh. That's definitely some future work, but it's definitely already a good step into the right direction.
Just to pick it up, how much impact has the initialization? Because I think in the first paper, triangle splitting, you had like the traditional initialization from just a point cloud, like from structure for motion. And now you use the triangulation. So how much impact has that on the quality?
I think that didn't change that much. It was more that as all the triangles are connected initially, you just have more, you're taking a little bit the flexibility of each triangle away, because in triangle splatting, every triangle was just optimized individually and you could just move it as you wanted. But now with Triangle Splatting Plus, as everything is connected, maybe one triangle wants to go into one direction while the other triangle that's connected it wants to go to to another direction. So I think the initialization was not the main issue. It was more that you have more constraints on the triangles, which makes optimization a little bit harder. But I think for the initialization, it doesn't change that much.
And on actually then when you start to prune, from what I recall, you take a pretty aggressive like pruning approach in Triangle Splatting Plus pretty early on. And then, obviously you have to densify. How you strategize that densification strategy when you have pruned so hard up front?
Yeah, so we just had like a lot of issues. If we don't prune triangles out, then what happens is that if you increase the opacity, at some point you end up with like floating triangles, which get like a super high, or which are eventually getting fully opaque. Then you just end up with like fully opaque triangles in the middle of your scene, and it just looks really bad, and you have just so many floating triangles. So we just had to do like a strategy where we just prune out all the triangles, or like quite aggressively, such that we just remove all those triangles that might end up being just floaters.
Are there maybe things which are worse represented with triangles or with this approach than, for instance, with Gaussian splatting? So how about thin structures like grass or thin foil or like wires? Is this harder to represent, or where does triangle splatting fail where Gaussian splatting is maybe better, and vice versa?
If you increase the opacity over training, such that eventually you end up with triangles that are fully opaque, I think you are able to better reconstruct like small details that if you, for example, use 2D.js and then you extract the mesh later, I think you lose more details as with Triangle Splatting Plus, because you are optimizing for a final mesh for like 30K iteration, and that's like your main objective, to have like a good visual quality. So most of the time, triangle splatting can better reconstruct like fine details than some other mesh extraction Gaussian splatting method. But the disadvantage then is that the mesh does not look as clean as if you extract it with some other Gaussian splatting post-processing mesh extraction pipelines. I think just for details and novel view synthesis, like mesh-based novel view synthesis, I think the details look better.
And on the primitive count, is it like more expensive? Do you need more triangles to represent the same object, or is it less?
No, I think it's way less. I think like for those large scale scenes, most of the mesh-based extraction methods that also extract the background, I think they have like 4 or 5 times more triangles than what we have with Triangle Splatting Plus or with mesh splatting. So
Yeah,
it's
and I think
definitely memory-wise, it's much, much better.
potentially what could be helpful too is to give some like context too about like you're saying grounding it compared to like Gaussian splatting on both like memory footprint and also the rendering capabilities too, because it's pretty shocking some of the frames or frames per second that you're able to hit using triangle splatting.
Yeah, I mean, the biggest disadvantage of Gaussians, if you want to render it in like a game engine or like a game engine, you have to do like all this color accumulation over all the Gaussians, which is just like super slow. But if you have like fully opaque triangles, it's just super fast. Like the first triangle you hit, you immediately know like whatever comes behind, we don't care. And so you can just like render everything so much faster. And that's also like one of the big advantages of Triangle Splatting Plus and mesh splatting is that if you have like limited computer resources or just like a very, very small GPU, you can still render it at a quite fast speed. But for Gaussian splatting, if you have like a couple of millions of Gaussians, it's getting quite difficult. While for mesh splatting or Triangle Splatting Plus, it's still easily doable.
And your follow-up work, you mentioned it already, was mesh splitting. So what did it add to Triangle Splatting Plus? So what was the innovation in mesh splitting?
Yeah, so one of the issues with Triangle Splatting Plus was that if you do the initialization of the Delaunay triangulation at the beginning of the training, there are not many triangles in the background, because if you use Colmap, like the point cloud that you start with is quite sparse in the background. And so we just had like pretty much no triangles in the background. So the idea that we had was to do for 15K training steps, just do triangle splatting, such that triangles can move around the scene, and such that we can also populate the background and have many more triangles also in the background. Then after 15,000 iterations, we just run Delaunay triangulation to get like this fully opaque, this fully connected triangle, like connected triangle mesh. And then we just optimize it for another 15K. But this time we already have many more triangles in the background, and the quality is just better.
Do you think if you would dance initialize Triangle Splatting Plus, you would arrive at something very similar and you don't do the hard pruning?
Yeah, I think if you would have a good point cloud initially, I think then you could probably immediately do it. I think there's still a couple of optimization differences between mesh splatting and Triangle Splatting Plus, but overall, like the idea and everything is very similar. So I think if you start with a dense point cloud, you can probably just skip the first 15,000 steps and just do the optimization or like the Delaunay triangulation immediately and just optimize for another 15K. And and the point cloud doesn't need to be perfect. We also tried to just add some noise to the vertices after 15,000 iterations to see how good does the point cloud actually need to be before running Delaunay triangulation. And you can actually add quite a lot of noise to the vertices, and the model is still able to recover. So even if the initial point cloud is not perfect, that's still it should still work.
This episode of the View Dependent Podcast is brought to you by RadianceFields.com, the best place to stay up to date with the world of Radiance Fields, and Lichtfeld Studio, the open source reconstruction platform. Build it yourself for free or purchase the binaries and start processing your splats today. Now, back to the episode. Compared to, say, like the triangle splatting to triangle splatting plus to then mesh splatting, how does the both opacity and smoothness values evolve over time? Because those are two different parameters that you started to really like refine as your research continued, right?
Yeah. Yeah, so for triangle splatting, the triangles could just pretty much do whatever they want, and the smoothness parameter and opacity was just optimized such that just like the visual quality looks as good as possible. But for triangle splatting plus, we then decided that what we do is we add a regularization, which just pushes the opacity towards having higher values, and the same for the smoothness parameter, such that at the end of the training, the regularization is just so much that it has to be like fully opaque triangles. And then over training, we just remove all the we have like a linear like we start by removing or pruning out all the triangles that are like below, let's say 0.1, and then over training we just increase this value, and everything that's then below this threshold is just removed, and eventually we remove, like at step 29,000, we just remove all the triangles that have an opacity below 0.9. And then for mass splatting, we did a completely different approach. We just manually increased the opacity and the sigma, such that the model could not really learn those values, but they were just overtraining, just increased manually without that the model can learn them. So the model was pretty much just learning the vertex position and the color. And the opacity and the smoothness were just from very soft and semi-transparent triangles automatically moved towards fully opaque and sharp triangles.
And so now that you have them all connected in mesh splatting, like what does that actually begin to enable for you?
I think the nice thing is that now you can just train like a very large scale scene. At the end of the training, the visual quality looks quite nice. Pretty much everything is connected. Like it's not perfect yet, so there's still some research to do. And you can just extract it. You can just use it in a Blender or like a game engine. And you can also extract easily objects, because if you have, for example, a segmentation model, you can just, let's say, click on the table, and then like if you have the mask of the table, you immediately know each triangle that is or is sitting on the mask. You immediately know that it's part of the table, because there's like no color accumulation. Like for Gaussians, it's a little bit more difficult, because you don't know if it's now really part of the table or if it's maybe like a Gaussian from the background, which still has some influence on the pixel. But with fully opaque triangles, you immediately know that if it's on the mask, then it's part of the table. So it has like a lot of nice downstream applications that you don't necessarily have with Gaussians, except if you maybe do some post-processing, extract the mesh, and do some additional steps.
And after the mesh splitting, I think you went back to Gaussians or to circles, which are basically 2D Gaussians. So now you were tweaking like the primitives. You started with convex primitives, then went over to triangles, and now you're back to Gaussians. Why?
I mean, I'm not really back to Gaussian. It was like I did mesh splatting and Nexels at the same time, so it was not really that I now came back to Gaussians. And it's also not fully Gaussians. There's still this gamma parameter which can make the Gaussians like really sharp, such that you end up with like a quad or like a rectangle. So it's not like a fully return to Gaussian splatting.
So what is the core idea of the Nexels paper? So what is different between, yeah, I mean, you mentioned a little bit that you can change the shape of the primitive and it becomes a rectangle, for instance. But what is the difference between like regular Gaussian splatting and the Nexels approach? What does it different, and what are the benefits?
Yeah, so one of the disadvantages of Gaussians is that the geometry and the appearance are tied together. So let's say you have like a very easy geometry, like let's say a table. If you still want to represent it with Gaussians, you still need a lot of Gaussians to really like get the texture right. Even though the geometry is really easy and you could just represent with a single primitive. So with Nexels, what we are doing is we are texturing the Gaussians, or like the quads, so you can easily place a much larger primitive to places where the geometry is easy, and then just simply texture the Gaussian, and then you can just reduce the number of primitives by, I think it's quite a lot, by 10 of 20. So it's like a very big gain, especially for like indoor scenes where you have a lot of structured geometry like walls, floors, tables. For outdoors, it's a little bit less, but it's still quite a big gain.
Going back to triangle splatting very quickly too, I saw recently that Microsoft actually pushed native triangle splatting support to Babylon.js in version 9. And so I was curious if you are aware of which version of triangle splatting is supported, but also like why, to talk about like why it's important for these various libraries and game engines to begin offering support for these representations.
So I'm not sure which version they included. I haven't checked it yet. I didn't have the time to do it yet. But it's definitely like super, super important, because I think the biggest advantage of Gaussian splatting over triangle splatting or mesh splatting is like this insane community of people that are working on Gaussian splatting. There are just like so many papers coming out every day, and like the progress that Gaussian splatting is doing is just very impressive and just insane. Well, there's just like a small number of people working on triangle splatting, working on some other primitives. So the field is just moving much slower, even though the primitive might have some advantages over Gaussians. So it's like very nice that triangle splatting is now slowly getting included in some libraries, because it's just pushing much more the research community to also work on triangle splatting and some other primitives.
And I have to imagine that, like, researching a direction that isn't quite as popular as, say, like Gaussians, for instance, as a primitive, must be a bit of like a challenge to do. And so I was curious of, since you have pursued many different primitives and found success in actually doing this in research, what advice you'd give to students who are pursuing things that perhaps aren't the hottest item or trendiest thing?
I think that's exactly what you should doing, right? I think there's so many people working on Gaussians, and it's just so difficult to do some work that really get recognized by the community. There are just so many Gaussian papers coming out every day, and it's really difficult to have a paper that really has an impact, or that really like the community actually sees the paper. So I think if you do some other things that other people are not doing, it's like, I think it's just a big advantage, because you just get much more recognition, and people usually always find it quite nice to see stuff that's different. So for all the PhD students, I would definitely say they should try some different stuff, and not just do like not doing what everybody is doing, but just trying some other stuff, and doing new stuff. I think that's much more interesting than doing whatever like what everybody is doing.
What do you think are the biggest challenges in this field currently? So in the Nexel paper, you showed like basically how to reduce the number of primitives, but there you have also like a neural aspect. Which what does it exactly do in this paper? The neural aspect. The goal was a little
Yep.
bit like to separate the geometry with the appearance, right? So my question is basically, what are the challenges currently in this field? So like doing the separation like of a geometry appearance also for Gaussian splatting, or in general, what do you think? What are the future avenues?
Yeah, so for Nexel, what we did was just have an MLP who predicts the color of the Gaussians, and in that way you can just have, instead of just having RGB or spherical harmonics, you can really have like a much like a texture of the Gaussians, which then just enables you to have like much larger Gaussians, which then can also cover much more area, and you can just remove the number of primitives by a lot, because you just can just represent much more with a single primitive than if you just have spherical harmonics, which is also, I think, a very nice direction for mesh splatting, because if you have like the opaque triangles, I think it's very difficult to really get like high visual quality, because you don't have this smoothness between multiple primitives, which gives you a nice color. So I think if you can do texture triangles for like the fully opaque mesh splatting stuff, I think that could be like a really nice direction. If you then just also fix the self-intersecting of the triangles and improve a little bit the connectivity, you end up pretty much with a really nice mesh, and I think that's definitely one of the end goals. Unfortunately, I don't have the time to do it anymore, but it's definitely a really nice direction. Otherwise, I think for Gaussian splatting, I think there are like still a lot of quite interesting directions. Like all this feed forward stuff is really interesting to just skip all this optimization and just do it like in one go. I think that's like really interesting. And then also like combining it with all this diffusion model and image generation, such that you can reconstruct worlds or scenes that you don't like, where you just maybe have a single image, or which you can just describe, and you can just like build a Gaussian spreading world.
I'd also like to talk about now, you finished, your I guess formal education, and now you actually joined the team at SpAItial, and you showed a early preview of your first model Echo in, I think, mid-December of last year, and I was wondering if you might be able to talk a little bit about the work that you're doing there as well.
I'm not sure how much I can share in what exactly we are doing, but basically the main idea that we have is that you can just describe a world of like your room or like your kitchen, or give an image as input, and we then want to reconstruct it such that you can just explore it as you want. You can edit it, you can change stuff, and you can just create 3D worlds that you can easily explore based on just like a single text prompt or based on a single image.
What applications do you see in this area? Because there's like this big community who's taking thousands, 10,000s of images, photos, and tries to scan an area just to reconstruct reality. And if you have like such a world model where you have like one image as input and maybe a prompt or a couple of images, you cannot reconstruct reality, right? So it's something which the model will come up because you cannot see around the corner, right? So this is never matching reality. So what are the different use cases you see for those two types of different approaches?
I think there's like a lot of use cases. The first one is it's just so nice to just input an image and then you can just like explore this created world. It's just so much fun. But also like if you, I don't know, if you want to redesign your house or like a room, you can just input it and you can edit it until that you really like it. So it's like, yeah, you can just like visually just rebuild like your kitchen, change stuff, change the color, add a new table or whatever you want, and you can just immediately see how it looks like. And I think it's just so much easier as if you would just buy a new table without ever testing it or seeing it in your kitchen. But also for like robotics, if you want to simulate stuff in like 3D worlds. Also, last time there was a journalist that contacted me because he has like a couple of images of some historic events, and he just wanted to reconstruct it in like 3D, such that you can explore those 3D worlds, but you cannot go back in time. So he just had like a couple of images, and then the idea was to also like build a 3D world of this historic event or building. And I think also use cases like this are super interesting. So I think there are just so many doors that are opening that you can use those world models or like those 3D reconstructions based on like a single image or just a description.
Do you think that this will replace the traditional reconstruction in the future, or is that just a different application?
I mean, if you want to get something that really looks like the place that you want to reconstruct, you probably still need enough pictures to reconstruct it correctly. But if you just want to reconstruct something and you don't care 100% if it's now perfectly matching the reality, I think then just a couple of images is more than enough that you can still get like a super nice reconstruction, even though it might not be 100% perfect or like 100% how it looks in reality.
So something like the construction industry or the geospatial industry, where they really need like objective and ground truth, either measurements or just certainty about what is located in a physical space. You think that that's probably not so much a use case for like world models compared to, say, if you wanted to then simulate like a crane moving through a construction site or something like that.
I think eventually we will get there, but I'm not sure if it's already doable right now. But I think it's definitely something that eventually we will get there, such as like a couple of images and to still get like a really nice reconstruction.
So I guess in the end, it doesn't matter which reconstruction method you have, if your representation is convex, convexal, or is it triangle or Gaussian splat. In the end, it doesn't matter, I guess, for world models.
I mean, it depends also of the use cases or like for what you want to use it. If you, I don't know, have like a VR headset which just runs on some limited computer resources, maybe triangles might be better because you can just render like the same number of triangles much faster than the same number of Gaussians. But if you have like a lot of computer resources, then maybe it's not such a huge difference which primitive you are using. I think it always depends a little bit on the use case that you have. But I still think that we need like for the next year still like some primitive to reconstruct scenes. And I don't think that like a fully image generation or video generation will get us there in the next few years. I think it's not consistent enough. Yeah.
And so kind of expanding upon that, like what do you think might that future might look like?
I think we will still be in the direction of like Gaussian splatting, triangle splatting, or whatever primitive we want, because I think one of the disadvantages with the diffusion model is that it's not consistent enough. If you, I don't know, leave a room and you come back, there's not 100% guaranteed that the room looks exactly the same as it looked like 5 minutes before. But with splatting or reconstruction, you exactly know that if you are coming back to the room, it looks exactly as it was looking 5 minutes before. So I think that's like one of the big advantages that you have with all this reconstruction, Gaussian splatting, is that you just have this consistency, which you don't have for like all these generation models. And also probably splat, like Gaussian splatting, you can still render it on a laptop and it looks decent. While for like all the diffusion model, they are also getting better, but you still need much more computer resources than what you need for splatting.
Having worked with a bunch of different primitives now, do you have a favorite that you think has like potentially a higher ceiling compared to another, or just general personal preference?
So emotionally, definitely convex splatting, because it was like my first paper. It was like the first time that I started 3D, and I still remember like the first time that the forward and backward pass was working, and I could see how the convexes were slowly moving towards the ground truth. It was just super nice. So emotionally, it was like 100% convex splatting. But I think like triangle splatting is still the better primitive and like the better choice over convex splatting. Or like all this triangle direction, it has just many more advantages over convexes. So emotionally convex splatting, but realistically, I definitely think that triangles have a higher chance.
Yeah, it's super exciting to see how this field evolves. And I think you gave us a really nice overview of your work, what you did, and what other primitives are available, what the advantages are compared to Gaussian splatting, which completely dominating everything right now. So thank you for this overview and having you with us.
Yeah, thank you very much. I really enjoyed it. It was really nice meeting you, and I really enjoyed it.
Yeah, no, we really appreciate having you on, and I think that we're going to be returning very shortly with more updates and more interviews with people who are doing really great work in this space. Some of which I think you've actually worked with. So we're really looking forward to being back and showing the rate of progress in the research world for lifelike 3D through the various Radiance representations. So thank you so much for coming on, and yeah, we will be back soon with future episodes. Oh, and also before I forget. If you're looking to process reconstruct any scenes, I definitely would recommend that you go and download my co-host Janusch's Lichtfeld Studio, which is totally free and open source as well.